Welcome, everyone. Next up, we have Dr. Turkalj to talk about the Fraunhofer project in a little bit more detail. Ivica did his PhD in pure mathematics from the Technical University at Dortmund. Then he worked for a couple of years as an actuary at an insurance industry, and later shifted to quantum, and now he's working as a quantum researcher at Fraunhofer ITWM. And today, Ivica is with us to talk about the project, which we are doing in collaboration with Womanium QSL and Fraunhofer. And all of you have the chance to participate and work well in this project to win a lot of exciting things at the very end. Over to you, Ivica.
Yeah, many thanks to Womanium and the organizers for the opportunity to present our project here today. I'm Ivica Turkalj. I'm a mathematician working at the Fraunhofer ITWM, which is a German research institute for applied mathematics. And I will give a short introduction to our project, which is about the applicability of quantum computing to problems in industry. And more specifically, our project is about anomaly detection using quantum computers and how production processes in industry can be improved with it. I will delve into the topic in more detail shortly, but first I would like to introduce you to our partners and your partners you would work with as part of this project. Our project is a current research project that is being funded by the German government. We are a group consisting of research and industry partners, and on the research side, we are supported by two universities, the University of Berlin and the University of Stuttgart, and also two Fraunhofer institutes, the Fraunhofer Focus, which is active in the field of information and communication technology, and the Fraunhofer ITWM, which is, as I said, doing research in applied mathematics. And on the industry side, we have DB, which stands for Deutsche Bahn, that is a national railway company of Germany, and Umlaut, a consulting company that is active in aircraft construction. And as I mentioned, we are working together on the question of how quantum computers can help in the application of anomaly detection. And let me briefly explain in a very simplified way what anomaly detection is all about and why it is an important topic for our industry partners. So modern production processes generate very large amounts of data. And this data can be used, for example, to optimize processing steps or to automate quality assurance and integrate it with the manufacturing process. And as an example here in the picture, such data could look like this. On the x-axis, the data points are simply numbered from 0 to 1,000. We can imagine that 1,000 small parts were produced for the manufacture of an airplane. And the y-axis measures how much the manufactured part deviates from some specification. And of course, each part will always have a small deviation, but as long as this deviation is within a tolerable tolerance limit, there will be no problems during production. And if we draw the tolerance limit in red, you can see that most of the parts are below this limit. And however, a few cases are outside the tolerance range, and the use of these parts could lead, for example, to safety problems in the future production processes. So the aim of anomaly detection is to find a mathematical model adapted to the available data that detects and recognizes outliers, such as these 3 points in the image. And of course, in this particular example, it's very obvious which points are outside the tolerance limit, but in real-life applications, it's not so easy to determine whether or not a deviation has occurred. So often it is not even clear how to select the tolerance limit. So the task of the model is not only to detect anomalies, but to define a suitable range for when something is considered an anomaly. And the industry is very interested in the development of such models because they have a major impact on profitability. So for example, by identifying early signs of equipment failure, companies can perform maintenance before a breakdown occurs, and thus minimizing unplanned downtime. Also, preventive maintenance is typically less expensive than emergency repairs. Thus, early detection of anomalies helps to avoid costly breakdowns. And detecting anomalies can prevent dangerous situations by identifying safety hazards before they lead to actual incidents or accidents. So to come back to our project research, we will develop models for the use case of aircraft manufacturing. And yeah, and I mean, aircraft manufacturing is an industrial sector where the safety issue just mentioned plays a critical role. And the data we will be working with are images, images of manufactured parts that need to be checked of errors. And our aim is to explore the extent to which quantum computing methods can support us in this task. And as often, industry relevant applications of quantum computing are almost always hybrid applications that combine classical software and implementations of quantum circuits. This means that classical algorithms and quantum algorithms are used alternately. So the classical algorithm generates data, and this data serves as input for the construction of a quantum circuit. And then the quantum algorithm generates an output, which is passed to the classical algorithm and back and forth. So this is the typical scenario for industry applications. But to be a little bit more specific, in this project, we will be using quantum neural networks. So this is a special kind of these algorithms with this hybrid property. But I mean, I don't have enough time to go into technical details about quantum neural networks, but I'm sure there will be some lectures during this event where the topic will be discussed in more detail. And also, if you look at the tasks that you have to complete for this project, you will see that they are completely designed to familiarize you with this topic. So no previous knowledge of quantum machine learning is expected. Instead, a large part of the task consists of introducing you to this subject. So task one, for example, is about getting used to the technical handling of the API that we use in the project. So we are working with PennyLane, and they are excellent tutorials that you should take a look at. The next task, or the next two tasks, are about learning the basic workflow in quantum machine learning. Here, the individual steps that occur constantly when working with machine learning models are explained. So the typical workflow is, first, you convert some classical data into a form that is suitable as input for a variational quantum algorithm. Then a parameterized quantum circuit is designed and implemented. And finally, you have to decide on a measurement procedure whose outcome encodes the result you are interested in. So task 2 will guide you through this procedure. In task 3, you should show some creativity and develop your own small quantum model that reproduces some interesting function, in this case, the sine function. This means you can experiment here, try out different quantum circuits, try out different measurement patterns and see what works best. And there are theoretical reasons why sine function should be easy to approximate. So I think you can get a good result by trial and error. And the last task is actually a little more difficult. It's about trying out something which is more closely related to the real life industry use case from the project. So as in task 3, it's about developing your own model, but the difficulty is that you have to think a lot more about pre-processing the data. So the data is available in the form of images, as I mentioned, and it's a non-trivial task to put them into a form that can be passed to a quantum neural network. So this will be a major challenge to get this model running with the data available, but From our point of view, task 4 is more of a bonus task for more ambitious participants. So just have a look and see what you can do. Yeah, all right. I think that's it from my side. Thank you very much.